Alright, are we live? Hello? Let's see. Alright, it's a little later now. Hello and howdy doody. Hope everybody's doing well. Okay. Let me just check the phone quickly. Oh, I gotta respond. I have to forgive me. What do you call it? I was going to go on a trip and ended up not going on the trip. And so I told some folks I was going to go, and then there was plans I was going to make, and I didn't make those plans, and I have to follow up with those folks. But I think we'll get back to that. I'll solve this problem first, then I'll respond. But yeah, actually, I remember my math teacher telling me that when I was younger. He was like, "How do you tell something similar?" He was talking about his kid. He's like, "How do you tell your kid the difference between lying and a change of plans?" When you were gonna do something and plans changed. Is it lying if you told your kid you were gonna do something but situation changed? Anyway, yeah, hopefully we're not lying. And the folks that we talked to, they understand when I explain that plans changed. Anyway, so to come back to this problem, yeah, I got some explaining to do. That's okay. Verify preorder sequence of binary search tree. So we did spend some time pondering this question, and I came up with a solution. So what we're looking for is, so we already solved this, right? I guess the first thing, we already solved it. What we're looking for though is a solution that's using constant space complexity. And if you look carefully at the discussion, you'll notice linear time complexity. So this problem, what I've done right here, excuse me, this is what divide and conquer algorithm. It's not linear time. It's at best, and what is it? It's actually, it might be linear. Take that back. I don't know what it is. I'm actually not sure. But it is using linear space, because the recursion that we're using creates a stack, and that uses some space. I think it's, I don't know, what is the, I don't actually know how, what the runtime complexity is for this. I want to say it's actually, might be linear. It might actually be linear time, and the reason for that is each iteration takes your range that you're operating on, splits it into two pieces to iterate on those two pieces, and removes one element from that iteration, specifically the head. So basically it takes the head, takes the middle piece, takes the, I'm sorry, it's not linear. It's n log n, because this routine is that's logarithmic. So there is a logarithmic step at each point. So it's n log n. Yeah. Okay. Yeah. But I think actually if this was a constant time operation, then it would actually be a linear time program. But anyway, so this is n log n, and it uses I want to say, I don't actually know how much stack space it uses. I want to say it might be linear, the amount of space. But I think there's a way to do this in linear time and constant extra space, and I'll try to do that now. I'll explain what to do. So the idea is we're gonna try to take this. Yes, let me explain the problem. Given an array of numbers, verify whether it is the correct preorder traversal sequence of a binary search tree. You may assume each number in the sequence is unique. Consider the following binary search tree. And you get one here, and this one 52613 doesn't work, and 52136 does work. So the algorithm that I'm going to describe, the idea is that we're going to visit. Did you try following the binary tree? What's up, Yuki? Welcome back. Hello, hello. Welcome. Oh, I wanted to say about why I've been deleting your history. I don't know if you caught that. The reason I was saying I deleted previous VODs because I had answers to very hard questions that the people on the website actually said, please don't ruin it for other people, so don't publish the answers. And the other thing was, where my history. And the other reason is that I don't think my videos where I'm just pondering stuff are super popular. I don't think people really like to watch me talk about. People don't really like to watch me talk. Just like sit, lay down on my bed and think about problems. So that was your answer to the question. But do you check your history for videos? go back to them. I tried doing the easiest problem on this website, and I couldn't understand anything. Really? Yeah, you do. You do. I mean, there's nothing wrong with that. I guess it's fair. I do that too. I mean, I don't do that too much, but. All right, hold on. We'll help you. We'll help you out in a minute. We'll go to the easy questions in a second. But let me. Which one? Wait. Okay. We'll review one of the easy questions for you, but because I appreciate that. That's awesome that you tried a problem. But let me solve this one first. I'll come back to it. But yeah, actually, what we're gonna do is not just try to follow the binary. This kind of is trying to follow the binary tree. This is very much like similar to this approach. But the approach we're gonna go for now is actually so. The property that needs to be true at every point is that there's sort of a head node, then there's some left binary subtree where all the values need to be less than the head, and then there's a right binary subtree where all the values need to be, oh sorry, that's the left one, all the values are less than, and then there's a right subtree where all the values are larger than the head. That property needs to be true at every point. So for 5, it's true with 2, 1, 3, and 6, right? So that's the left subtree and that's the right subtree. And then for 2, it's true where the 1 is the left subtree, which is smaller, and 3 is the right subtree, which is larger. So you see 1 is smaller, 3 is larger, and so this is true. And now the thing that's interesting about this property is that everything to the right of that subtree, once you find this point that's larger than this guy, everything over there, it's always going to be larger than that head node. So you can actually just say there's got to be some either 0 or more values that are less than the target you're looking for. So 2 and 1 would be just one value in this case, and then everything after that has to be larger than that value. And so that's true for 2, and then for 1, there's no left or right subtree, so it's just everything to the right of it's larger. And then for 3, again, there's no left or right subtree, so again, everything to the right of it's just larger. And then for 6, there isn't anything to the right of it, and but yeah, it also has no left or right subtree. It's just everything to the right of it being larger, and there's nothing to the right. So that's just true. So it's true for all of those points, so we return true. Here, though, you'll see a problem. 5, 2, 6, everything to the right of 6 should be larger. However, 1 is not larger than 5. In fact, 1's not even larger than 2. And so you immediately run into a problem. And the idea behind this algorithm that we're going to use is we're going to go ahead and check this property by saying we're going to push each value as we go from left to right. We're going to push it into a stack of numbers. And once we see a number, as it's decreasing, as numbers are decreasing, we push it onto the stack. As soon as we see a number that's larger than the last value on the stack, we're going to pop the values in the stack until we get to a value in the stack that's larger. So for instance, for 5 and 2, you'd push 5, push 2, you see 6, you'd pop 2, you'd pop 5, and you'd push 6. And once you've popped each value you pop, everything to the right of those values needs to be larger than that, as you saw, as described. So everything has to be larger than 2, and then since you pop a 5, everything actually also has to be larger than 5 too. So as soon as you see a 1, you have a problem, return false. So that's immediately how that would be handled by this algorithm. Push 5, push 2, push 1, you see 3, you pop 1, you pop 2, everything has to be larger than 2. You push a 3, so now 3 and 5 are on the stack. You see a 6, it's larger than 2, you pop 3, you pop 5, you push 6, and then you get to the end and you return true, because you didn't violate anything at all. And that's it. That's the whole algorithm. Obviously, if there was more stuff after 6, if there were like, you know, if you made these numbers like 50, 20, 10, 30, and 60, and then you had like a 55 after 60, you wouldn't pop. You wouldn't actually. You would just push 55. You would push 55, and then you would end, and then that would be it. Because that would be sort of the left subtree for the 6. So you could put a 55 here between 50, 60, and 55. Wait, I have to go. My boyfriend needs me. I'll come back next stream. Also, you should check out Unknown Cheat CSGO. You might enjoy the epic reverse engineering game cheating. Yeah, sure, okay. Take care, Yuki. I'll talk to you soon. Yeah, I appreciate you coming by and saying hello. Appreciate it. I'll keep that in mind. I'll keep that in mind. I'll, by the way, I'll actually, I have to ask you what the problem was that you looked at. But, the next time, yeah, I was gonna say I'll go over one of these problems with you, or what have you, or I would do it on stream, but I kind of would want to know which problem specifically you struggled with, and then I would go through it, so that way, you know, I don't want to do the wrong one, the one that you're not interested in, or one that you haven't seen. So feel free to give me one. But yeah, thank you for coming by and saying hi. Appreciate it. I appreciate it. All right. So now. So okay, so this problem, let's take a look. Let's take a look. What we're going to do, we don't need recursion anymore. Don't need any of this. We're going to say there's a global minimum, which is going to be int max, or int min. We're going to say for int I equals 0, I is less than preorder dot size. We're going to say val is going to be preorder of I, and we're going to say if we actually, so just do edge cases, or sanity check edge cases. And this isn't, we're actually going to not use this as a constant anymore. I'll explain that in a moment. Let's see. So obviously if there's only one element, we just return true. Or if it's empty, we return true. So the size needs to be at least two elements. And I'll explain why in a moment. Just call this st for a stack. And we want to say stack push. We're going to take preorder of I, or 0. And then we're going to start this at 1. Yeah. And so this value. And we're going to say val is that, top is st, should be top, right? Should be non-empty. Actually, we'll call it t. Just call it t. It's either. So we're gonna do something interesting here. We're gonna say st dot empty. As long as the stack is not empty, we're going to set t to be the top. Otherwise, we're going to set it to int min. Is that right? Is that what we want to do? Is that what we want to do? I'm actually not sure what we want to do here. Let me just leave that out for a moment. That's a tricky thing. So what we want to do now is Okay. We want to compare this value to the stack. And first thing we want to say is if val is less than the global min, or even equal to, then return false. When we get through the whole thing, return true. So we're going to say while st.empty, while the stack is not empty, and val is greater than the stack top, right? So we get the top of the stack, we compare the value to it. If the value is greater than the top of that stack, we're going to pop the stack, we're going to remove that value, we're actually going to reset the global min to the maximum of what's at the top of the stack and what the global min already is. Right, we're going to update the global minimum, we're going to pop from the stack, and then we're going to push onto the stack this new value. So while the value is larger than what's in the stack and while it's not empty, we're going to keep updating the minimum and then push our new value onto the stack. Yeah, that's the idea. It's got to be less than the global minimum. You can run into some issues if it's not less than, if it's less than or equal to, you can run into some issues. So I think if there's anything else we need to do here, I think this is it. Let me just see what happens if we do this. Okay, looks like it's accepted. Alright, how do we do here? Oh, looks like it's correct. I think that's it. Yeah, that was the whole... See if we can find any test cases that fail. Let me see, we had, okay. So we said we can add stuff, right? We can do like 70, we can do like 55, so that could be 55, 70, something like this. We could do 80, 90, 100, right? You could do that. True at the end. But then you can throw in like a 12 or 23, right? And that should fail. Okay, alright, we'll go for it, see how we do. Oh, got there. Nice. Sweet, so I was right. Okay, yeah, pretty simple once you figure it out. Yeah, I realize this seems kind of weird, but that's it. Now what you want to do here is we can modify this to not use the stack. We can actually use a pointer in the array as we move from left to right that represents the stack. So I'll show you what that looks like. So let's call it ST. and the initial value will be index 0. It'll actually be index 1. And so popping the stack, we decrement. Pushing the stack, we increment and then set the value. Yeah. So we start off at 0. And then we say while stack isn't empty, which is actually going to be while st is greater than or equal to 0, and val is greater than, the top is going to be preorder of st. Right? That's the top, which is preorder of st. And then popping is equivalent to st minus equals 1. So we pop. Pushing is we increment st by 1, and we set preorder of st equal to whatever that value is. Something like this. Let's see how this goes. Still correct. And now we don't need to use a stack at all. Let's go for it now. There you go. Boom. How about that? How do you like that? How do you like that? 100% faster than every other solution. So super fast. And doesn't use any extra memory, right? No extra memory. There we go. There we go. Does destroy the original vector. However, yeah, there we go. That's the challenge, the extra challenge. So there's your round 2. So I like them apples. I like them apples. That's fun. All right. So thank you again. Thank you all for watching. I will talk to you soon. Have a good rest of your day. I'm going to respond to some folks. There were some people I was going to look into, I guess, make plans with. And like I said, I don't want to be dishonest with them, but I basically I told them I was going to go on a trip, so I couldn't get together, and then actually my plans have changed with regard to that. So yeah. Thanks again. Talk to you soon. Enjoy the rest of your day. I'm going to keep going, I think, here, but I'll be gone for a few minutes. So yeah, take care. Take care. Just going to full screen for a moment before I end the video.